Okay, so the plan for today is to continue going over work and energy and kind of talking about everything that was worked on in the last lecture, reviewing the concepts, but also doing some practice with it. So we'll start out simple with concepts. We'll do a couple of smaller practice problems with just singular forces, and then we'll go over a bigger practice problem with multiple forces and overall work and things like that to kind of look at the big picture. So that's the plan for today. And then, as always, I try and leave some time at the end for any questions that you guys might have. Um, so that's on the agenda. So we're going to start with a review of the topics. What did we remember about work and energy? What was gone over in lecture? So I'm going to give you guys a few minutes here. Take a look at your notes. Think about anything that you learned in lecture yesterday, and just put a few things in the chat that you think are significant about work and energy that you mentioned. Is that work is equal to force times displacement. And to be kind of specific, it's equal to force dot product of displacement. Another way of looking at that is that force and displacement have to be parallel to each other for work to be produced. So I use a little parallel symbol, not necessarily the correct physics way to write it, but it helps me keep in mind what is dot product versus cross product and things like that. So work is equal to force dot displacement. I also see that the unit of work is a joule. Is a joule. And can anybody tell me what the units of a joule are? What do you guys know about this? So we use J to represent joule. And then if we're thinking about it, what actually goes into a joule, we can see that if work is equal to a joule, force times distance is equal to a joule. So we could think of it as a Newton times meter. Or in terms of the simplest units, we could go down to kilograms. So we're looking at a Newton is kilogram times meters over a second squared times meters. So kilograms times meters. So joule is the simplest unit. That's how we would use, that's the unit we would use to describe work. But just to check your units, to check that things are dimensionally consistent, that's a good way of breaking down your units so you can figure out what cancels out and what doesn't. Okay, another comment in the chat. We see that there's different types of energy. So somebody said kinetic energy. There's also spring energy. Different types of energy. We've got kinetic. We have potential energy, which can be grouped into two categories. We have gravitational potential. So that's things like the energy that's produced by something having height. Like if you throw a ball in the air, it's got potential energy when it's coming down. And then we've got elastic potential, and that's what we call spring energy. And that's, things that inherently have energy. When you pull them further, energy is produced, and that's what the spring energy is. So when we get more into conservation of energy, we'll get further into those. But it's good to keep in mind that energy does exist. We know that kinetic energy is equal to 1/2 times mass times velocity squared, which is a general equation for that, and is something that's going to come up a lot. Can anybody tell me about the relationship between kinetic energy and work? There is an important relationship between that. Work is equal to the change in kinetic energy. So also another way of looking at things, if you're not looking at things in terms of distance and force, then work is important. Then kinetic energy can be another way of calculating work. I see somebody said that if there's no, if it doesn't move, it doesn't do work, and that's definitely correct. Because of that, if it doesn't move, there's no distance. If there's no distance, force times 0 is just going to equal 0. Also, if there's no force acting on the object, if there's no external forces, no parallel forces, it's also not doing work. So kind of work is not always assumed. Certain conditions have to be met. And we want to keep that in mind when we're going over our examples today. So this is just kind of general concepts, equations. It's a start to the topic. Work can be negative. Work has direction. If the force is going in the, in an opposite direction to the distance, you can have negative work on an object as opposed to positive work. One example that was, I think we saw in class yesterday, was there was a weightlifter lifting up a bar as opposed to putting it down. And, when you're putting the bar down, it's almost like it wants to go downwards because of gravity. So it's doing all the work for you, as opposed to when you're lifting it up, energy's going into it versus out of it. It's, you have very different scenarios. So direction is super important when calculating work. And we'll definitely cover that today in the examples. So this is just a starting point. Keep this in mind when we're going over our practice problems today. So, individual force here, we have the block is going to be moving a distance of 10 meters horizontally to the right, as we can see in our distance vector. There is a force of 20 newtons, which is applied at an angle of 120 degrees relative to the positive x-axis. So we want to know what is the work done on the box, specifically by the force F. So there may be other forces acting on this, but we're only looking at force F right now. So we've talked about equations, we've talked about concepts, we've talked about kind of what conditions need to be met between the forces and the direction and things, all of this. In the chat, I see 100, negative 100 joules. So there seems to be agreement on the magnitude, but not necessarily the direction. So we are going to take a look at that as well. From the review earlier, we said that work is equal to force dot distance, which also means that force and distance have to be parallel. Now, clearly our distance in this case is not directly parallel to our force, but that doesn't necessarily mean that there isn't a component of the force that's acting in the same direction as distance. So if we were to break up our force into components, what we can see is that the x component is parallel to the distance, and that's the part we're going to look at. The y component is acting perpendicular. It's not parallel. It's not helping with the work that's being done by that force. So it's not important to the current situation. So we're really looking at the force in the x distance for this one. So we're going to say that the work due to force F is equal to the parallel force, which is going to be this x component here, and that's going to be not theta, but let's just call that phi or some other angle. This is going to be F times, and this is the adjacent one, so cosine, not necessarily of 120 degrees, but of 180 degrees minus 120 degrees. You could just say that's 60. You could do this differently. I'm just going to subtract from 180 to get this remaining angle. So that is our force. And it's going to be times our distance, which is, the direction is set for distance. We don't have to break that into components. So that's 10 meters. Now, if I say that F is 20 newtons, plug that in. I'm left with 20 newtons times the cosine of 60 degrees times 10 meters. And I get that the work due to the force is equal to 100 joules. So we got that in the chat, but now we have to look at direction, which is something that we kind of haven't used up until now. So we could look at this as kind of which directions is everything going. The x component of the force is going to the left, which we typically see as negative, so I'm going to assign that negative. The distance is going to the right, so I could assign that to be positive, meaning my answer would be negative 100 joules. Now, this just tells me that the force and the direction are going in opposite directions. They're working kind of almost against each other. The force is slowing the block down. It's not helping its movement, and that's why it would be negative. The reason why I didn't use 120 degrees is because this right here is not a right angle. It doesn't support, it doesn't really support the same things always. So I prefer to find an angle that is consistent with my right angle triangle. That being said, it's not always wrong to use 120 degrees, to use like that wider angle. It's not incorrect. I like to work within the right triangles because it tends to just work a little bit better sometimes for physics, and it gives me more information. But yeah, so either way, We all got 100 joules, which is correct, but we want to make sure that we call it negative because negative work is done. The force is acting against the distance that the block is moving in. They're going in opposite directions, so it's negative work. And that's the end. So our second problem here, we have a box that moves 20 meters horizontally as a force of 40 newtons is applied downwards. What is the work done by force F? So again, I'm going to have you put your answers in the chat. How much work is done by force F in this problem? So this one, slightly simpler problem. It's more about understanding the concepts than doing the math. And I see everybody got 0 in the chat. That is correct, but let's look at why it is 0. Again, we're looking at force dot distance, which means they have to be parallel. As we can see, the force here is directly perpendicular to our distance. There is no component of this force that would be parallel to our distance. They are at an exact 90 degrees. This clearly is not going to work for our math. It's going to give us a 0 so that we can say that the work is done as 0. So keep that in mind when you guys are working on problems in the future. If you have a force that is acting perpendicular to the distance that is traveled, you don't have to worry about work being done. If there is a force that is at an angle, some component might be doing work, so you can't necessarily count it out just because it's not parallel. There will be components, so kind of keep that as the separation between those two types of forces. For our third problem here, we have a box which moves 5 meters horizontally when force of F is equal to 10 newtons is applied at an angle of theta is equal to 60 degrees. So again, we're solving for what is the work done by the force F. So kind of similar to the first problem, but slightly different. How would you guys solve? It seems like you guys reached consensus. I see in the chat, everybody got 25. Let's go over this, see how we get to this answer. So work is equal to force times distance, parallel again. In this case, we can see, again, the force is at an angle, but there is a component of it that will be parallel, which is the x component. So we can take the force, which is 10 newtons, and we want that parallel component, which is the adjacent angle, so times cosine of 60 degrees, which is the angle given, and times our distance, which is parallel to that, which is 5 meters. So we can see they're going in the same direction, so positive work is being done. It's helping the movement, it's not working against it. So we can say that this is equal to 25 joules. So that is correct, you guys got it. So the key point of doing these 3 separate problems was to have one with negative work, one with no work, and one with positive work, to give kind of more of a concrete example of what each one looks like and how you can identify when that's happening. We have a 5 kilogram block, which is moved up to a 30-degree incline by force of 50 newtons, parallel to the incline. The coefficient of kinetic friction between the block and the incline, so that's mu, is equal to 0.25. How much work is done by the 50 Newton force in moving the block a distance of 10 meters? So that's the first question. Just what is the work done by the 50 Newton force on the right? And then the second question is, what is the total work done on the block over the same distance? So you know the distance is 10 meters, and you're going to look at this in 2 parts. First, what is the work done by the 50 Newton block? Second, what is the work done overall by all the forces acting on this block? And that's where we get kind of more into understanding what's acting on a block and in which direction. And part A, we're looking at the work done just by the 50 Newton force. So we can say the 50 Newton, as is said in the problem, is directly parallel to the ramp. And we also know that the block is moving up the ramp, so the distance is parallel to the ramp too. So I can say that my full 50 Newton force without components is equal to the parallel force, and my distance, which is given, is 10 meters. And my 50 Newton force is moving up the ramp. And we can see from the problem, because it says a 5 kilogram block is being moved up a 30-degree incline, that the block is also moving up the ramp. So the block and the force are in the same direction. So we're looking at a positive 500 joules of work here. So that's just the first part, individual force. Now we have to look at all of them. Just here. So one of the first ones we can look at is friction, which I see. Again, as we know, friction is always going to act parallel to the surface because that's how it works. And it's always going to act opposite to direction. So we know that it's going in the opposite direction. We know that it should be doing negative work. So my frictional force is directly parallel. I don't have to break it into components, but I do have to think, what exactly is friction equal to? So, I can say that friction is equal to mu n, which we know. But in this case, the normal force is not equal to mg. It is only equal to mg if we're on a flat surface. In this case, the equivalent force that's going downwards is actually mg cosine of 30 degrees. This isn't the same thing as me taking my component of the friction force. The friction force does not need to be broken into components. I'm just finding what normal force is equivalent to and then plugging that in. So my friction force should equal mu, which is 0.25, times mg, so that's 5 kilograms times 9.8 meters per second squared. All of this we know, we've done this in forces, times cosine of 30 degrees. Okay, and then, as always, I can't forget to multiply it by my distance, which is 10 meters. I know these are going in opposite directions. I could say that this is a negative force, or I can just say that it's negative work because I know they're working opposite to each other. But this should be equivalent to negative 106.1 joules. Okay, so that's one more force figured out. Now, I don't know, it's not part C of the problem, but for the next part, I see another one that was mentioned is mg sine of 30. So that is the x component of our weight. Yeah, so weight might be acting downwards, which is not parallel, but the x component of our weight is parallel to the ramp. So mg is equal to our component, which is mg sine of 30. And this is going down the ramp. It is a negative force times our distance, which is 10 meters. So I'll leave that as that. You guys know you're plugging in 5 kilograms for mass, and you're plugging in gravity is 9.8, and you end up with negative 245 joules. So we're kind of slowly getting these components and putting them together. The normal force, as we know, is directly perpendicular to our ramp. Perpendicular forces to the distance do not produce work, so the normal force is a work of 0. We already know that our 50 Newton force produces 500 joules. That we already calculated, but that is one of our overall forces. And that is all of the forces that are acting on it. We've considered what forces are there, we've considered which direction, considered their components. So to answer part B, all I have to do is take the sum of these, which is going to be negative 106.1 joules minus 245 plus 500. And we get that is equal to about 149 joules positive. So the work done by the 50 Newton force was actually much higher than the overall work done on the object, because some of that work was basically being undone by things like weight and friction, which are making it harder to pull the box up the ramp. And that actually makes sense based on what we know about how these forces work. They are working against each other. Weight and friction are going to be working against something that's pulling the ramp up. So reminder, there is a session on Monday still. We'll keep going with work and energy, and probably get more into like kinetic energy and things like that on Monday and discussing that. We'll keep going through this. 4:30 p.m., the typical time. And if you guys have any questions, feel free to email me.